Have you ever wished you had a crystal ball? I mean, who hasn't, right? Well, what if I told you that a special kind of math can actually let you predict the future? No, not the lottery numbers, sorry. But we're talking about the future of real, everyday things, like how quickly your coffee cools down or how fast a population might grow. Today, we're going to unlock that power.
So it all kicks off with a really simple question. You've got a hot cup of coffee. We all know it's going to cool down to room temperature eventually, but could we predict its exact temperature at, say, 10 minutes from now? Or 20? Well, the answer is a big yes, and the tool we're going to use isn't some fancy lab equipment. It's just an idea, written in the language of mathematics.
And this is our puzzle. Now I know, it looks a little intimidating with all those letters, but don't let the symbols fool you. That dt on the left, all that really means is the rate of change of temperature over the change in time. So you see, the equation doesn't tell us the temperature directly, it only tells us how fast the temperature is changing. Our whole mission is to turn that description of change into a direct prediction of the actual temperature.
Okay, to crack this puzzle, we need a special technique. And I want you to think of it like sorting laundry. Right now, all of our math variables, the t's for temperature and the t's for time, they're all mixed up in one big pile. We've got to get all the temperature stuff on one side of the equation and all the time stuff on the other.
Now, this sorting trick only works for a certain kind of problem. They've got a fancy name, separable differential equations. But it sounds way more complicated than it is, I promise. All it really means is that the rate of change, dy dx, can be written as some function of x multiplied by some function of y. That multiplication is the secret sauce. It's what lets us neatly pull the x laundry apart from the y laundry. And here's a perfect example of why that multiplication is so important. On the left, because the x and y parts are multiplied, we can just use some simple algebra to move things around and get them into their own piles. Easy. But look at the one on the right. The x and y are added together. They're all tangled up like a ball of yarn. You can't just pull them apart neatly. So, for our method to work, we need that sortable kind, the one on the left. So, we start here with this jumbled equation. The x's and y's are kind of hanging out together. Our first job? Sort them out. And voila! This is what we're aiming for. With a little bit of algebraic shuffling, we've moved everything involving y over to the left side and everything involving x to the right. The laundry is sorted, the piles are neat. Now we can actually get to solving this thing.
All right, let's move on to the recipe. Once you get this four-step process down, you can solve any of these separable equations. It's a reliable, repeatable method for building our mathematical crystal ball.
So here it is. Step 1 is separate. We just did that. Step 2 is integrate. Now, integration is basically the mathematical antidote to a derivative. It's the thing that undoes that whole rate of change part. Step 3 is solve. This is just good old-fashioned algebra to isolate the variable you're looking for. And finally, step 4, apply. This is where we plug in a real-world fact, like the coffee's starting temperature, to get a super specific prediction.
Okay, we've got our 4-step recipe. It's time to go back to that cooling cup of coffee and actually put this method to the test. Let's see if we can really predict the future.
So, here's our puzzle again. The rate of change of temperature equals some constant, K, multiplied by the difference between the coffee's temperature, T, and the room's temperature, Tm. Let's fire up our 4-step recipe.
First things first, separate. We're going to treat that whole TT chunk as our temperature term and divide it over to the left side with dt. Then we move the time term, dt, over to the right. And just like that, all the t's are on the left, all the t's are on the right. Step 1 is done.
Now for the really important part, integration. Here's how to think about it. That derivative, dt, it tells us the slope or the steepness of the temperature change at any single moment. Integration is the process that adds up all those teeny tiny moment-to-moment changes to give us the original curve back. We apply this antidote to both sides, and that's the key to unlocking the actual temperature formula hidden inside. So after we apply the rules of integration, and then use some algebra for step 3, we get this. And this is absolutely incredible. Look at what we've done. We started with an equation about a rate of change. And now we have a formula, T of t, that will directly tell us the temperature for any future time t we decide to plug in. We've actually built our crystal ball. Now, that a you see there is just a constant that pops up during integration, and it's the key to our very last step. So what is this mystery A? Well, you can think of our formula as a generic prediction for any cooling object. To make it a prediction for our specific cup of coffee, we need a starting point, and that's step 4, apply.
We just need to measure the coffee's temperature right at the beginning, at time 0. We can plug that known value into our equation and solve for A. This locks everything in, turning a general solution into a precise prediction just for us.
You know, this isn't just a party trick for predicting coffee temperatures. This exact same 4-step method is used to model some of the most important processes in science, in finance, and all over the natural world.
For instance, the basic model for population growth, dp dt equals kp, is a separable equation. It just says the rate of growth is proportional to the size of the population. Makes sense, right? And the same logic applies to things like chemical reaction rates and even some financial models for compound interest. This little recipe we've learned has some seriously huge implications.
This whole thing seems almost too powerful. When we find a solution, can we be 100% sure it's the one and only correct future? Or could there be, multiple possible futures all described by the same starting equation?
For most real-world problems like our coffee cup, the answer is a pretty comforting yes. The future is unique. This is true as long as the functions in our equation are continuous. Now, all that means is that the physics of the situation is predictable. The temperature of the coffee isn't going to suddenly teleport from 90 degrees down to 20 degrees. It changes smoothly. So as long as there are no weird breaks or impossible jumps, our mathematical crystal ball shows us the one and only path forward.
And really, that's the big takeaway here. We started with an equation that could only tell us how fast something was changing. By using this method of separation, we completely transformed it into a powerful formula that predicts what state it will be in at any point in the future. That's just amazing.
So the next time you're watching steam rise from your coffee, or maybe you're watching the balance of a savings account grow, look for that hidden pattern. Ask yourself, what's the rate of change here? You might just discover that the future isn't as mysterious as it seems. It might just be following the elegant logic of a separable equation.